Mel Sweetnam is the founder and director of Mamie's Schoolhouse in Eastern Canada. Going to stop that. She's a juried member of the Cape Breton Centre for Craft and Design, founder, I don't know how you say this, Unama Cape Breton Fibre Trail, and president of the Victoria County Arts Council. Mel is the admin of the global Natural Dye Education Facebook group, has a lot of members, including myself, and is now founder of the new Natural Dye Journal. She combines her lifelong fibre art studies, post-secondary studies in biology, and previous career in evidence-based research management to explore and teach a vast array of plant-based mordants and dyes, and an ecological stewardship approach to all fibre arts. Big welcome then, Mel. Thank you very much.
Thank you very much, Jenny. Can everybody hear me okay? Is the volume okay?
Yes.
Yeah, okay, great.
Yeah, fine.
Okay, thanks a lot for that introduction. Yeah, as Jenny mentioned, I spent a previous career managing public science policy, predominantly the design and delivery of academic research funding programs and studies. And I was heavily involved in the discipline of research transfer, which focuses on how to bridge the worlds of academic research and public policy. Since any of you who are familiar with scientific research will know that the language used by academics in peer-reviewed publications is often not very user-friendly, even for a highly educated but non-specialist audience. So I was involved in trying to make academic research accessible and applicable to real-world policy issues. And so while I'm not a scientist, my own education is in biology and then public health administration at the master's level, I spent a career immersed in promoting, enabling, and using evidence-based research. So that's the framework that I bring to my own natural dye practice. And I'm here today to talk about some work I've been doing exploring the potential to extract metal salt mordants from local plants. So before I actually get into the actual trials that I've been doing, I think it's helpful in the first instance to do a quick recap of what mordants are, as it will put the process and materials I used into a more comprehensible context. So what the heck are mordants? Mordants are metal salts. As many of you know, the actual term mordant comes from the Latin mordere, which means bite. And in the historic literature, the term is used pretty much exclusively to refer to metal salts. But nowadays, there's often a watering down of that understanding and a misattribution of other substances that, though they may have valuable roles in helping fibers take up natural dyes, are not actually mordants. So you'll often see people refer to tannins or to binders and sizing agents like soy as mordants, but they're not. Mordants are metal salts. And they're found everywhere in nature as well as manufactured. So I'm now on slide 4. I'll try to remember to mention each time that I move from one slide to the next. So if mordants are metal salts, what are metal salts? Well, a metal salt is the result of a reaction between a metal and an acid. And often in that reaction, hydrogen is released in the process. So I suspect that many of you have made your own homemade iron water, which is ferrous acetate. And so you will have actually observed this chemical reaction in front of your own eyes, because generally what happens when the metal reacts with the acetic acid, most people use white vinegar to make their own iron water, you'll see bubbles being released. And generally that's the hydrogen gas that's being released as a result of this reaction. I'm now on slide 5. And it's helpful to also know that there's a standard way of naming metal salt mordants or metal salts, and it can help you to understand the component metal and acid from which that metal salt was created. So generally the first part of the name of a metal salt refers to the metal that was involved in the reaction. And the second part of the name refers to the acid that was involved in the reaction. So why do mordants matter? Well, One of the wonderful things about metal salts is that they can form what are known as coordination complexes, which provide a very stable molecular structure that forms strong bonds between the fibers, the mordant, and the dyes. And one of the handy attributes of the chemistry of these coordination complexes is that once your dye is bonded as part of a coordination complex, the dye tends to become insoluble. It won't dissolve anymore away from your fibers. So of course we want our dye materials to be soluble at the front end of the process so that they'll dissolve in water, which is the carrier that we use for all of our natural dye processes. We use water to carry our scouring agents, our mordants, our modifiers, and our dyes around and through our fibers. But once the fibers have actually been dyed, you don't want the dye to actually wash out each time you launder your textiles. So one of the wonderful attributes of coordination complexes is that it makes all of those bonds very stable and removes the solubility from the dye component. So I'm now on slide 7. So as the admin of the Natural Dye Education Group, one of the questions that we field in the group quite often relates to safety and naturalness of metal salt mordants. There's a lot of people who are concerned about whether they are quote unquote natural. But that comes from a lack of understanding of how ubiquitous metals and metal salts are in nature. They're absolutely everywhere. Metals are naturally occurring elements in the universe, and we have a sizable number of them here on planet Earth. So they're very abundant in rocks and soils. This is the image on the left is Prince Edward Island, which is the island next to me, and it's famous for its incredibly iron-rich red soils. And aluminum and iron are respectively the 3rd and 4th most commonly found elements in the Earth's soil. And if you were to take a handful of soil, and this is an average, obviously there's variability in soils across the planet, but if you were to take a handful of soil, typically 7% of that soil by weight is going to be aluminum, and 1 to 5% of it is going to be iron. So metals and metal salts are not only natural, but they're incredibly widespread throughout nature. So historically, there have been a few different ways that our natural dye ancestors have tended to source mordants, and the first is from rock and soil. And we have pretty ancient historic records of those practices. The oldest surviving written record of the mining and sale of alum as a mordant for textile practice is from the famous histories of Herodotus 2,400 years ago. And there are plenty of other historic records since then, including many of the incredible commercial importance of metal salt mordants, particularly alum, as traded commodities in Asia, Africa, and Europe for millennia. And then also, I'm on slide 9, our natural dye ancestors also extracted mordants from some plants. There's less of a surviving historic written record on these, but there is some. So we know, for example, that in the tropics, the genus Simplicos, which is comprised of hundreds of different shrubs and trees, has been used for a long time by peoples in the tropical regions because of its high aluminum bioaccumulation properties. And some of you may be familiar with the Biodyes Foundation in Indonesia, which is a social enterprise that sells the leaves of particular Simplicos trees as a plant-based mordant. Very worthwhile enterprise to support. And then in the temperate regions, some of the, or probably the best known plant-derived mordant has been the club mosses from Lycopodium, which are not actually mosses. They're actually much more closely related to ferns. And there is a good historic record of their use throughout different parts of Europe. And I know people here on Cape Breton Island, which was predominantly settled by the Gaels during the Highland clearances from Scotland, who remember their grandmothers going into the forests here on Cape Breton to harvest Lycopodium to use in their natural dyeing. But nowadays, most club mosses are are very endangered. They've been completely extirpated in some areas. They tend to rely on a stable, mature forest ecosystem to survive and thrive. And as forests are cut down, there's less and less appropriate habitat for them, and they've also been overly harvested. So it's actually forbidden to harvest them in many parts of the world. And so I don't recommend that you go out looking for club mosses, because at this stage of our history, we just really need to leave them alone. So the third major way that our ancestors accessed metal salt mordants was through the use of the actual vessel that they did their dyeing in. So often dye pots were made from clay, and clay is a type of soil, so it would have contained whatever metals were in the soil that the clay was derived from. And also reactive metal pots, so copper, which is less reactive than a lot of other metals, but bronze and iron. And often in old dye recipes, you'll see strong acids that are used in the dye bath, which seem to have no relevance to the final dye color that's being pursued. The theory for a long time was that while they may not have understood the chemistry, our ancestors often observed that by using an acid in the dye bath, they were able to achieve better color and longer lasting color. And I believe that's because the acid was involved in a reaction with the metals in the vessels and pulled it into solution in a co-mordanting process. And I'll come back to that. So I've been interested in relocalizing my own practice as much as possible and my own supplies as much as possible, primarily in an attempt to reduce my own carbon footprint on the planet. And also because even though purchased metal salt mordants are perfectly natural and perfectly safe to use by a knowledgeable practitioner who's observing normal safety precautions, I have been concerned for a long time about the way in which alum in particular is produced. So alum is produced from bauxite, which is strip mined from topsoil. And topsoil is the top 5 to 10 inches of the Earth's soil. And it's basically responsible for all life on this planet. And in the last 150 years alone, we've actually destroyed over half of the world's topsoil. And we're on track to destroy the rest of it, pretty lickety-split. So the idea of using something that relies on the mining of topsoil, and that includes all of the usual adverse environmental impacts of any mining activity, hasn't really sat very well with me. And so, I've been thinking for a long time about whether there was a way to better identify and use bioaccumulator species from my own immediate environment. So I asked myself, what are the plant species that could be accessible to the home dyer that we could grow or responsibly forage ourselves? And I'm on slide 12 at the moment. And could metals within those plants be pulled into a mordant or dye bath, i.e. through the use of easily available non-toxic acids? Because you'll remember at the front end, I talked about how a metal salt is the result of a reaction between a metal and an acid. And so if the above, could be achieved, what would the process look like and what might the pros and cons of this approach be? On to slide 13. So there are a lot of bioaccumulators in nature, and we've actually been using that knowledge for many decades, primarily in respect to phytoremediation of industrial sites. So you're probably all familiar with former industrial sites that have been cleaned up by the planting of very targeted species that are able to pull toxic metals and other toxins from the soil out of the soil so that that land can then be used for other purposes. And also in recent years, there's been growing efforts in regards to a relatively new discipline known as phytomining, which is using fast-growing crops of known hyperaccumulators to extract metals that in ways that are much less harmful to the environment. So the image on the left is of a species in the tropics that is a hyperaccumulator of nickel, and it basically oozes nickel as its sap. On to slide 14. So one of the first things I had to do as I tried to pursue my questions was to try to learn as much as I could about the known bioaccumulators on our planet. And that was actually a really hard slog. There's not a lot of helpful information that's in the public domain. But the first resource that I found that was really useful was the Global Hyperaccumulator Database that is hosted by the University of Queensland. It's publicly available. Just search Global Hyperaccumulator Database and you can access it yourself. And it is an initiative of Australia's mining industry. And a lot of the companies in Australia are multinationals, and they have mining operations in many other tropical and subtropical regions of the world. And so the database, has been produced through that lens, and a lot of the species that are included in it are focused on the kinds of metals that are the product of mining operations. So it's by no means a comprehensive database, but it's the best one I've found so far. I then discovered that Canada also has its own bioaccumulator database, which is focused on the temperate species of my geographic region. But I didn't reach out to them until March, unfortunately. It's not a publicly accessible database. And by March, we were already in COVID lockdown. So they've got me on their wait list, and they're going to be sending me the CDs as soon as they can. So I'm very excited to have a look through that. There's also a short list in Wikipedia that you might want to take a look at. It's a good introduction to kind of the science of hyperaccumulation, but the list is far from complete. On to slide 15. So then, as I started to think about the acid component of the reaction, I had to try to pull up what I remembered from my organic chemistry days in my undergraduate degree many years ago. And I remembered the reactivity series of metals, which is an important framework for helping to identify the kinds of metals that might be extractable from plants through the use of an acid. And what the reactivity series of metals, this is slide 15, tells us, and the image is shown on the left here, is that there's this Goldilocks zone, this group of metals in the middle here that are reactive with acids. And what it also tells us is, like, the reactivity series not only shows us which metals are reactive with different solvents, but it also tells us what the hierarchy of reactivity is. So in the group of metals that are reactive to acids, those further down the list, such as lead or tin, are less reactive than those further up the list, such as zinc or aluminum. And that's helpful to know, because what it means is that, say you have a plant that is bioaccumulated lead and aluminum, and you expose that plant to a strong acid. What the reactivity series tells us is, all other things being equal, which they rarely are, especially in a home dyer situation, but all other things being equal, it's the aluminum that should preferentially bond with the acid, not the lead. So on to slide 16. And my screen has just gone blank. Jenny, can you tell me if you can see?
It said initial experiment, so yeah, we're fine. I can see it on my.
Okay, so I'm going to just flip to my other screen here so that I can go through it.
Oh, that's working. I can see it from here.
Yeah, but I can't. So.
Oh no! Oh no!
Yeah.
I can see it does say initial experiment. Oh yes, it's the circle, the circle arrow.
So I just tried to refresh. It's buffering. It's taking a while. Anyway, I can see it. I can see it. Yeah.
Let's refresh.
Okay. Yeah. It's slowly refreshing. I guess that's in keeping with one of my favorite adages, which is, when all else fails, follow the instructions. Okay, so anyway, on to my initial experiment. So having done some of my preliminary, research and reading and reminding myself of some of the basic organic chemistry that I studied so many years ago, I started to think about how I would approach my own test. But first, let's just do a really quick recap. So some plants can accumulate metals. Acids can react with some metals to create metal salts, and the resulting metal salt compound now has the properties of being soluble in water and of forming stable molecular bonds with natural dyes and fibers. So on to slide 18. So I reviewed a number of different bioaccumulator species that were available to me on my property. I live on a large acreage in literally the middle of nowhere. And luckily I'm surrounded by many different plants. And I decided to use Plantago major, broadleaf plantain, in the first instance. It's a known bioaccumulator of iron, cadmium, and lead, but there is no lead in my soil, so it can't bioaccumulate it. I wasn't sure about cadmium, but I did find out as a part of this process. And I chose it also because I had done tests before on the tannin capacity of Plantago major, and I knew that it contained a high concentration of gallic tannins, which tend to be very light colored or clear. And so I wanted to choose species for the experiment that would produce the clearest possible mordant so that they wouldn't influence the dye results any more than necessary. So I chose Plantago major. And I used a very high weight of fiber. This was the first time I was trialing this, and I had really no way to know what would be an appropriate weight of fiber to use of either the bioaccumulator or the acid species. But, I knew that the portion of any metals that were bioaccumulated within the leaves were going to be a very small percentage of the overall mass. So I went high with 400%. So now on to slide 19. And I chose as my acid highbush cranberry, Viburnum trilobum. I have a lot of different berry species and also other acidic plants on my property, and I tested the pH of a number of them over the years. And highbush cranberry is by far the most acidic berry that's directly or easily available to me. And with a full extraction, the pH dropped to 2.9. From these berries, which is comparable to the pH of the industrial acids that are used in laboratories that are doing phytoextraction of metals from plants. So it seemed to be, a pretty applicable acid to use. And I used the berries at 200% weight of fiber. So on to slide 20 and then 21. So the process that I actually followed was that in the first instance, I simmered the berries on their own, and that was to extract the acid, but also to degrade the anthocyanins. So as many of you know, the reds, pinks, blues, and purple pigments that we see in many berries, fruits, and vegetables are comprised of a class of dye compounds known as anthocyanins, which are not very stable and degrade easily. I didn't want a false influence of the color from the berries on my fibers, so I opted to try to degrade the anthocyanins right at the front end as part of the process of extracting the acid. And then after doing that, I added my chopped Plantago major leaves and simmered them together for about an hour. And we know that tannins, or that heat tends to darken tannins. And so if you look at the image on the left, the upper fibers are those that were mordanted in the plant-derived mordant bath. And I think that pretty much all of the color that you see is a result of the heated tannins and not an influence from the berry anthocyanins. So then I added the fibers and I kept them just below a simmer for an hour, took them off the heat, left them to cool overnight in the bath, and then rinsed and dried them. I also did control samples prepared traditionally, so cellulose oat gall tannin and alum acetate and protein potassium aluminum sulfate. On to slide 22. So prior to dyeing, I had taken baseline metal readings of the water to be used for the bath. And then after the 24-hour extraction, I did the same. And I had to order specialized laboratory water testing kits for this because you can't really get these kinds of measures from the kinds of kits that are available at hardware stores, etc. And so I was interested in testing the three metals that the literature told me were bioaccumulated by Plantago major: iron, cadmium, and lead. And while I was at it, I thought I might as well test the aluminum content too. So I did find that the iron content doubled after the 24-hour extraction in the plant mordant bath. Cadmium and lead levels were undetectable before and after, and I knew to expect that for lead, but I wasn't sure about cadmium. But what really surprised me was the aluminum extraction, because Plantago major is not known as a bioaccumulator of aluminum, but there was a 5-fold increase before and after the extraction. So I dyed the fiber samples, heat for an hour, left them overnight to cool in the dye bath, rinsed and dried them. On to slide 23. So these are the results. So on the top image are the protein fibers, the bottom are the cellulose. On the top, it's wool on the left, silk on the right, and then within each pair of samples, we see the traditionally mordanted one on the left and the plant mordanted one on the right. So what you can see is that I got really good color from the plant mordant samples. It's different from the color on the traditionally mordanted samples, although not so much for wool. It's a pretty comparable color, regardless of the whether it was a traditionally mordanted or plant mordanted. With silk, there's a noticeable darkening on the plant mordanted sample. And with the cellulose fibers, the color is beautiful, but the plant mordanted fibers are significantly lighter than the traditionally mordanted ones. On to slide 24. One of the other dye baths that I tested was Coreopsis tinctoria, which is native to large parts of Eastern North America. And again, I got very good color from the plant mordant samples. And again, it was different from the traditional mordanted samples, but this time it was more different for wool. Whereas silk, if I hadn't have labeled them, I really wouldn't have been able to tell which was mordanted with which method. And again, for the cellulose, good color, but much lighter on the plant mordanted samples than on the traditionally mordanted ones. On to slide 25. So then I proceeded to do Lightfastness tests. So I was doing this trial in the dead of winter, which is something to experience in Eastern Canada. And we don't get a lot of hours of daylight each day. And so rather than doing kind of a conventional 1-month Lightfastness test, I decided to do 3 months. It was a south-facing window, but I did a full 3 months because I figured that was probably equivalent to the amount of UV exposure that a sample might get if I'd done it in the summer instead for just 1 month. So for Rubia tinctorum, to my eye, the relative degree of fading between the plant mordanted samples and the traditionally mordanted samples is pretty comparable. So for example, if we look at just the silk, the relative degree of fading of the silk plant mordanted sample is pretty comparable to the relative degree of fading of the silk traditionally mordanted sample. The one exception might be the plant mordanted cotton and linen. They might have faded a little bit more, and I'm going to come back to that because I've improved my method and I'm getting far less fading now. So I'll mention that again in a minute. On to slide 26. For Coreopsis tinctoria, this was really a surprise. Because to my eye, the fading on the plant mordanted samples on the top is almost not observable. It's really difficult to see any fading on the lower half of the plant mordanted samples, whereas the traditionally mordanted ones also did well, but you can see that the lower half are noticeably lighter than the top half of the traditionally mordanted ones. So this is a bit of a mystery to me because most yellow dyes in nature come from the flavonoid category of dye compounds. And we know that flavonoids have less fastness generally than dyes from other dye compound categories such as anthraquinoids or indigoids, etc. So I'm not quite sure how to explain why my plant mordanted Coreopsis tinctoria did so incredibly well even after 3 months in the sun. So on to slide 27. So some of the pros and cons that I drew from this test. Some of the pros are that, you know, I get to work with non-extractive mining sources of metal salts and acids that I can grow and forage myself, and I can still achieve really good color and really good light fastness. Some of the cons are that it's still quite difficult to find good information that's publicly available on regional bioaccumulator species. And it can be challenging for a home dyer to do really accurate tests of the metal salt amounts that are being created as a result of the reaction between a bioaccumulator species and an acid. And it's also difficult or impossible to extract just the metal from the plant. You know, you have to accept that you're working with a whole plant and all of the complex chemistry that plant is comprised of, and you're extracting a lot of things into your mordant bath besides the metals. And also, it's not really a pro or a con, but using this method results in a different dye palette. You know, it's beautiful, but it's different. And so if you're used to getting certain colors from using, you know, supplies that you've purchased from a dye supplier, so, you know, mined and highly purified alum, etc., you know, you're going to have to set aside your expectations of what the final color is going to be. It's an entirely different dye palette that you can achieve. It's still beautiful and still rich, but it's different. On to slide 28. So some of the next steps, I've been working on a number of additional tests where I've been varying some of the variables. So I've been looking at different bioaccumulators, different acids, different weights of fiber, different dyes, and also different process steps. And I've also recently started exploring some of my local mushrooms, some of which contain some very, very interesting constituents that have mordant potential. And I've had some very exciting results from those. And I'll be posting the results of all of these trials on my blog in the coming months. And I would really love to be able to partner with an academic lab that could do, you know, much more sophisticated testing than I can do at home of the before and after measurements and of a larger range of metals, and also of some of the other, you know, chemistry and chemical reactions that are happening in the mordant bath that just really aren't understandable to a home dyer and with the measurement tools that we have available to us. So that's my presentation. Thank you very much. And I just wanted to let you know that in my office in the team suite, on the right-hand wall, so this is shown on slide 29, there's actually a short video demonstration of how I actually did the extraction process for my very initial trial. So you might want to take a look at that if this process interests you. And Jenny, I just want to say thanks again so much for organizing this and inviting me to present. And thanks so much to the Royal Society of Chemistry for sponsoring the event.
That's lovely. Mel, that's absolutely fantastic. Thank you so much. And do go and look at that presentation. Not only is it a little movie, it's got music as well. It's quite professional. Wonderful. Mel, thank you so much. I am so glad we had you here today. And I'm sure there are going to be lots of people who are interested. Are there any questions? We'll do it the old-fashioned way with hands up, I think. No questions? It was a very comprehensive talk. Brilliant. Thank you very much. Oh, there's one. Who have we got up here? I can't see at this distance. Rachel. Yes, Rachel.
Oh, hi. I was just wondering, Mel said that she used leaves, and I'm just wondering, would there be benefits in actually using the whole plant, including the roots?
So that's a fantastic question. One of the things I didn't cover in the presentation, in the interest of time, was in the course of doing some of my preliminary research, one of the kind of concepts I came across in the academic literature was something that's called the translocation factor, and it's a way that scientists measure the degree to which a plant hyperaccumulates metals in the underground parts versus the above ground parts. So if you're comfortable with looking at the scientific literature, knowing about the translocation factor is a very handy kind of search term, and it can help you narrow in on those plants that bioaccumulate in different parts of the plant. For me, I was really interested in finding those plants that have a translocation factor that's greater than 1. And what that means is that they tend to hyperaccumulate the metals in the above ground parts of the plant, because to me, that makes it a more sustainable source of bioaccumulated metals. If you have to dig the whole plant up, that's not a very renewable practice. Whereas if you can find species that tend to bioaccumulate in the above ground plants, you can harvest those aerial parts without destroying the entire species. And so that was actually one of the reasons why I chose Plantago major, because it tends to hyperaccumulate or bioaccumulate in the above ground parts of the plant.
Okay.
Lovely, thank you. We've got
Thanks.
Brian and Susan with their hands up. I don't know if they're asking the same question. Brian and Susan?
Hello, hello. Yeah, this is not actually Susan speaking. This is Ashley.
That's Ashley, right? Okay.
And I just want to ask a question about the berries that you use as an acid source. And I noticed that there are many old recipes that include berries of some kind in the dye bath. And I wondered if that's where you got the idea to use the berries, or if you just thought that since they were generally tart, that you would try that.
Well, in the literature on some of the First Nations practices in North America, there's references to use of berries, but also to other acidic plants. Yeah, that had been at the back of my mind for a long time, and I kind of breezed over it in the presentation, but having read that in a lot of the historic literature, you know, I would scratch my head thinking, well, like, what's the role of the berry in this recipe? Because it doesn't seem to have a role in influencing the final color on the fibers. And so my suspicion for a very long time had been that our ancestors, as I said, they may not have been able to understand the chemistry of why it worked, but they could observe the fact that it did. They could observe that when they used a high acid material in a reactive vessel, that the color that they got on the fibers was better and lasted longer. And I think that's because the acid was reacting with the metals in the vessel, whether it was clay or made from a smelted metal. And so I think that they were basically creating a co-mordanting situation by using an acid that could react with metals and pull them into solution. That's my theory anyway.
Yeah, very good.
That's fascinating. Right, I think we've got 2 more over here. Donna.
Oh, hello. Thank you, Mel. This is great. I'm also from Canada in the West. And I'm just wondering if you are able to, when you get the information from the Federal Agricultural Department, that you could share it, or is it available to others?
Yeah, I'm not sure. They're only making it available on CD, and you have to, you know, kind of write to them to apply for access to it. And I'm not sure what the copyright provisions are on it. I'll have to wait and see. But to the degree that I can share information from that database legally, I will.
Sounds great. And then,
Hi, I've still
depending
got
on that, I'll check into it too. Thank you so much.
Judy.
Hi. Yeah, I'm also from Canada. I'm originally from New Brunswick, so in your neck of the woods.
Hi, JD.
Hi. You've partly answered my question already, which was about the knowledge of the local First Nations. And I'm wondering if you have any really local knowledge from Cape Breton about what the First Nations used for dye there.
Yeah, a little bit. You know, unfortunately, because of, you know, cultural dislocation and trauma, a lot of traditional practices, the knowledge of them has been lost. And the written record in particular is fairly limited. a lot of the best information on the traditional dyes of First Nations in Canada was actually collected by Hudson's Bay agents who often, live their whole lives within local communities and established respectful relationships, and were able to kind of observe the whole practices. And most of those records are held by the Hudson's Bay Archive in Winnipeg. And again, I had been planning a trip there, and then COVID struck, but I'm hoping to be able to access some of that information. But yeah, I certainly know a little bit about Mi'kmaq dyes, and I'd be happy to email you offline about that.
Thanks. Interesting.
And Brian, we have a hand still up there.
Yeah. It's quite well known that coreopsis and madder are affected by the pH of the bath. And I wondered whether you took pH readings of your natural dye bath concoction relative to, and also took the pH reading of the traditional method, and whether that could account for the quite different colours you were getting in between the two.
Yeah, it's possible. I'll have to pull up my my more detailed notes. I did do pH readings basically at every step of the process, and I've certainly done pH readings of the materials that I routinely use many times in the past, and also of my own water supply, which is very, very slightly alkaline. But there really wasn't a noticeable difference in the final pH reading of the dye bath compared to what I get with traditional metal salt mordants. They were relatively comparable. I'll try to dig up my notes and get the actual measures, and I'd be happy to send them to you.
Thanks for that.
Okay, we've got loads of hands up still, but I'd love to continue. Is Mariana here? Joan Ash, sadly.
Yes, I'm here.
Okay, are you able to get ready while we take a couple more questions?
Yes, sure.
That would be lovely. If you'd like to come up here. We've got a few people who still want to ask, and I think Debbie is one. His hand has been up for ages.
Yes, please. My question's about your water. What allowances have you made for your water, if any?
Well, so I teach, and my my ethic often when I teach and what I tell students is it's really good to be knowledgeable about all of the components of your dye bath or your mordant bath, and to do baseline pH measures, etc., just so that you have some understanding of how your final results are being influenced by the different variables. But I also think, it's important to use what you have. So I do collect rainwater for a lot of my dyeing, but I also live in a rural property with well water that is incredibly pure. And as I said, it's slightly alkaline, but I mean, really only slightly, usually measured between like 7.5 and sometimes 8. So it's the water that I've used in all of my other dyeing and that I use for the traditional metal salt mordant samples as well. So I wasn't using different water for different components of the process. I used the same water source throughout.
Okay, thank you.